Hello again, physics friends. This is going to be a brief video to talk through how to visualize and think about perturbed circular orbits. And basically, we're looking for a case where we have some effective potential that has a minimum, and at that minimum, we're going to have that minimum corresponds to some circular orbit. So let's say we have some effective potential. I'm just inventing some effective potential here. It doesn't actually correspond necessarily to some interesting physical situation. This particular effective potential has a couple minima. We'll pick one of them to focus on. And again, this is a potential as a function of distance from the origin, say. Or I guess in a two-body system, r would be the distance between the two bodies. And let's say we have a circular orbit at that location r naught. And you can see this is quite a shallow potential, but it is a minimum, right? And so near that minimum, we expect to have stable oscillations. The particle would move back and forth, and its radius, the distance between the objects would be growing and shrinking, growing and shrinking. So what does this look like? Well, first of all, let's think about the case where we have exactly a circular orbit, okay? And if we plot, if you'd like, the position, the r coordinate of the object as a function of angle from 0 to 2 pi, okay? For a circular orbit, that plot is fairly boring, right? So for a circular orbit, that means no matter what the angle is, the distance from the origin is exactly r naught, okay? So it's a flat curve here. Now, maybe I should have started with this, but let's specifically think about a one-body system in which we have, in the xy plane, we have an object, let's call it a mass m, some distance from the origin, so we have a position vector r, and r with r, the non-vector r, is equal to the magnitude of r. So if this object is moving in a circle around the origin, that circle will have a radius of r. Okay, and in this case, we can think about the angle relative to the x-axis. That angle is phi, and if this particle makes one circle, one orbit, phi goes from 0 all the way around to 2 pi. The actual shape of the orbit would be a circle, but we can make a plot of distance from the origin as a function of angle. For a circular orbit, that would be a flat line. So when we talk about a perturbation to a circular orbit, we're basically saying instead of the particle always being a fixed distance r naught from the origin, the particle will oscillate back and forth about r naught, sometimes further than r naught and sometimes closer to the origin than r naught. And we quantify that by saying the distance from the origin as a function of time is equal to, on average, r naught, but we allow for some deviations, and we call those, say, epsilon, relative to r naught. And the condition here for small perturbations is that epsilon is much smaller than r naught. So what that corresponds to is a plot of position versus angle that will be not a flat line, but rather a line with perturbations to it. And in the limit of small oscillations, those perturbations will be sinusoidal, okay? So when we allow for these perturbations, we don't expect to see a flat line here for r versus phi, but instead we expect to see some perturbations around r naught, sometimes closer, sometimes further away from the origin, okay? So if you'd like, we can use this idea and basically take this graph and wrap it around to connect the endpoint with the starting point, and that will give us a graph of the shape of the orbit in the xy plane. So if we take the xy plane here, and we're going to plot on it from theta equals 0 to 90 to 180 to 270 to 360, we're going to take this red line for the circular orbit and map that onto this plot. So we're starting at theta of 0. We're always a fixed distance from the origin. So I'm doing my best here to draw a perfect circle of radius r naught. okay? That corresponds to the unperturbed orbit. And you'll notice that the starting and ending point are the same. So for a circular orbit, it's always going to be the case that the distance from the origin at phi equals 0 is the same as the distance from the origin at phi equals 2 pi. In other words, after one orbit, you end up back where you started. Makes sense? But now we're going to allow for deviations from that orbit. So on top of this red circular orbit, I'll draw a purple graph. And what I see here is the way I've drawn it, it's not always going to be this way, but the way I've drawn it is that the perturbed orbit matches the circular orbit at phi equals 0. So what that means here is at phi equals 0, I start on the circle, and then I move further from the origin. Okay, so what that means in this graph is I'm going to move outwards from the circle, and then I oscillate about the orbit. Okay, so I'll be further from the origin, closer, further, closer, further, closer, further, closer, and so on. And let's see, here I've drawn 1 cycle, 2 cycles, roughly 3 cycles per orbit. So I'll go out and in, out and in, out and in, like so. So I go out and in, that's 1 cycle. Out and in, that's 2 cycles. Out and in, and that's about 3 cycles. Now, I've intentionally been vague about what happens at the very end, okay? So I haven't actually closed this purple curve, and I've been intentionally vague about that because I don't yet know if my purple curve closes in on itself. I don't know if this condition is true. It's certainly true for the circular orbit, but I don't know if it's true for the purple orbit. So one of the things I want to talk about is how to tell if it closes or not, okay? The other thing I want to talk about is to be clear, when we talk about the deviation from the circular orbit, we are talking about the separation between the purple and the red curves, right? In the radial direction. So at some points in the orbit, epsilon is 0, like where the purple and red cross, there's no deviation. But at some points, there's the maximum deviation and then largest negative deviation. Purple is inward from the circular orbit and so on. So what we can see here is the circular orbit forms a baseline about which the perturbation is oscillating. And so this epsilon is really a periodic function, this epsilon of t. It's something like a cosine or a sine, so we could call it, say, a sine of a function of phi, okay? So as phi goes from 0 to 2 pi, this function cycles. And the rate at which it cycles, the number of oscillations per orbit, is determined by this omega. This omega here is the radial perturbation. So omega radial tells us the frequency of radial oscillations. Okay. There's another frequency, and that is the frequency of the circular orbit. In other words, how long does it take for phi to change by 2 pi? So the other quantity that we care about here we'll call the orbital frequency. Okay. And now that we've introduced the orbital and the radial frequencies, this will allow us to figure out if this purple curve closes in on itself. Okay. So if you can fit an integer multiple of purple cycles for every orbit, then that means the purple curve will close on itself, and the end point will equal the starting point. You'll come right back to this point. So in that case, if we have a radial oscillation frequency that's an integer multiple of the orbital frequency, that means you're going to have more radial oscillations, more than one or more radial oscillation per orbit, and you'll have exactly an integer number of those oscillations per orbit, which means you're going to come back exactly to where you started. In other words, you'll have, in this case, maybe 1 cycle, 2 cycles, and then if this was exactly 3 cycles, you would end up exactly where you started. your distance from the origin at phi equals 0 would be the same as your distance from the origin 2 pi later. And in that case, this purple curve would be closed, and we call that a closed or even a stationary orbit, meaning that this every 2 pi, you get exactly the same path traced out over and over and over again. There's two other possibilities. One is that the orbit doesn't close after one cycle, but maybe it closes after the second cycle or the third cycle or the fourth cycle. And in that case, we can express that as omega radial is equal to a ratio of integers. So p and q are integers. And that ratio would be multiplied by the orbital period. So if you have, let's say, 1 radial cycle every 2 orbits, or 3 radial cycles every 2 orbits, then it would take more than 1 orbit to come back to where you started. But eventually you would come back to the same position on the x-axis, and then that pattern would repeat. So that situation might look like the following. So here's an example of a circular orbit in red and a perturbation from that in purple. And what we can see here is the radial oscillations have a frequency that's 1.5 times the orbit. That means you have 1.5 cycles of the radial frequency of the radial perturbation for every orbit. So if we start here on the x-axis, let's say we go out, we come in, and we go out, but we finish only a half cycle, so we're going in again. So notice we're not retracing our steps yet. So then we go in, out, in, and then now we start retracing our steps. So you have to go around the circle twice before you retrace your steps, but the orbit is closed after those 2 cycles. So 1 cycle, 2 cycles, repeat. 1 cycle, 2 cycles, repeat, and so on. So we can say that this orbit is closed, and any orbit that has a radial oscillation frequency that's an integer ratio times the orbital frequency will be a closed orbit. Notice also that this brings to light an important condition. The condition for the system to repeat its orbit after 1 cycle is not just, it's not only that the distance from the origin at phi of 0 is the same as it is 2 pi later. That's one condition. But you also need the velocity to be the same, the radial velocity to be the same. How do I know that? Well, in this case, we're moving outwards when we start, and then inwards, and then outwards. But then when we get back to where we started, we're at the same position, so we satisfy the first condition, check. But notice now we're moving inwards, so we're not following the same trajectory we did in the beginning, we're going inwards, and then it's not until the second cycle around that we satisfy both conditions. So we satisfy the position, but not the derivative, but the derivative at 0, phi 0, is the same as the derivative 4 pi later. And so that means we're going to close on ourselves eventually. And here eventually means after 2 cycles, not 1 cycle. So you might be wondering, are there any orbits that just simply never close? And the answer to that is yes. If you can't meet this criteria, if the radial oscillations cannot be expressed as a ratio of integers times the orbital frequency, then the orbit will never close. So that's called a ratio of integers is called a rational number. So if the radial oscillation frequency is an irrational number multiplied by the orbital frequency, then you'll never close the orbit. So if this ratio, omega radial over omega orbital, is irrational, the orbit just will never close, and you'll get something that looks like this. So here we have that red circular orbit, and then we have, in purple, a perturbed orbit that is oscillating about the circular orbit, but it never closes in on itself. So let's see, in this case, I just kind of made it up, but let's see, we have 1 cycle, 2 cycles, 3 cycles, so between 2 and 3 cycles per orbit. So that would be square root of 5 is a number that's somewhere between 2 and 3, and that is an irrational number. Okay, so let's say the radial oscillation frequency is the square root of 5 times bigger than the orbital frequency. In that case, you might have an orbit that looks like this purple one. So it oscillates in and out, but it never repeats on itself. And you could do this forever, and you're never going to come back to exactly this original path that we started on. Okay, in which case the orbit never closes. The final thing I want to say here is, are there techniques for drawing these orbits in a way that's easier? And my answer to that is yes. So if you look at this case, I like to think about it as drawing it out linearly and then wrapping it on itself, right? Because this red curve is this red curve with the ends connected together, and the purple curve here is the purple curve here with the ends connected together. So let's just do a couple practices of how to actually make this accurately. So let's start with this specific example where you get 3 radial oscillations per 1 orbital oscillation. Okay, so in that case, we would have a plot of r versus phi from 0 to 2 pi that looks like this. We'd have r naught in red, that's our circular orbit, and in purple, I'll draw my perturbed orbit. And we got to have 3 cycles. So we can kind of mentally chop this up into 3 sections of equal length. And we're going to get 1 cycle in each of these 3 sections. Like that. And so if we actually want to draw the orbit in the xy plane, then we're going to start, as always, with our circle. And then we're going to imagine wrapping this plot up about that circle. So again, I can do the same thing. I'm going to split this into thirds. So I take my 2 pi, I chop it into 3, so that's 120 degrees per cycle. Like that. So I can indicate the same thing here. I have 0 degrees, 120 degrees, 240 degrees, 360 degrees. And I need to draw 1 in-out cycle. Like, so we go out, 0 crossing, and then in, and then out, 0 crossing, and then in. It's a little bit tricky to draw. Then we go out, out, 0 crossing, in. So there's our perturbed plot. In this example, let's assume that it takes more time to make a radial oscillation than it does to make 1 orbit. So in that case, if we plot r of phi from 0 to 2 pi, we have our circular orbit, and then we will only get a half cycle over that 2 pi. So that tells us immediately that our orbit is not going to close on itself after 1 round, but it'll close on itself after 2 rounds. So let's draw our circle. We're going to start here. We're going to have a maximum deviation. We're going to have a maximum deviation half an orbit later at pi, that's here. So we're going to be maximally deviated. And then we're going to come back to the origin, but with a other velocity. So we're going to start moving outwards. Okay, we're going to start moving outwards. We're going to grow in our deviation from the circle. And then we're going to come inwards, but not cross the red line until we get back to the origin. Oops. Like so. And then once we cross the red line, now we're inward. So we return to our starting point, but we haven't repeated the orbit yet. We have to go once more around before we repeat the orbit. So we're going to be maximally deviated inward when we get, that's pi, 2 pi, 3 pi later. And then we come back to the origin, and then we repeat from there. So this is a perturbation that takes 2 orbits before it repeats. 1, 2 orbits. okay? So as a final example, let's consider the case where we're going to have a lot of radial oscillations for every orbit. And in that case, as you might have guessed, we're going to start with our plot of distance from the origin as a function of angle from 0 to 2 pi. We're going to have our circular orbit where the distance is constant. And on top of that, we're going to have a lot of oscillations. So when we move to the plot of the actual shape of the orbit, we're going to have this circular orbit. And then from there, we're going to have a lot of oscillations. And I find these ones a lot easier to draw because locally the red curve is pretty straight. So I think this kind of looks like one of my favorite objects in the world, which are cupcakes, or at least the tin of a cupcake or the wrapper of a cupcake. So in the limit where you have a lot of radial oscillations, you end up with a perimeter that kind of looks like the boundary of a cupcake shell. Well, hopefully this video has given you a sense of how to draw orbits in the xy plane, the shape of the orbit, and you can think conceptually about drawing it linearly, r as a function of angle, and then wrapping it into a circle. And we've also talked about whether or not an orbit will close. This one closed after one cycle. In this example, we didn't close until 2 cycles, 1, 2. And in general, you might not close ever if the ratio of the radial oscillation frequency and the orbital oscillation frequency is an irrational number. It cannot be expressed as a ratio of integers. And then in the limit where you have a very high oscillation rate radially, you end up with this kind of cool frilly looking cupcake structure. All right, well, hopefully this has been helpful. Until next time, take care and be well.